Welcome to Energy Session 1.0, Energy Basics. This EMSI training section provides an introduction to energy basics. Your presenter is Matthew Barham. This module will provide a refresher of the basic knowledge surrounding energy, power and cost, and their relation to performing an energy-based analysis of a residence or SME. So, what is energy? Simply, energy is the ability to do work. And work is the transfer of energy from one form to another. Energy is what we use to change the world around us, whether it be from sleeping to walking or by using electricity in our everyday lives. This transfer of energy is based on the law of conservation of energy, which states that energy can neither be created nor destroyed. It can only be converted or transformed from one form to another. What results from this is a huge number of classifications and ways of measuring and quantifying energy. The international system of units attributed to energy is the joule, but there are other ways that can measure energy depending on its type. Forms of energy. Energy can generally be defined in two ways, either kinetic, which is moving energy, or potential energy, which is stored energy. Potential energy is stored energy. It exists in many different forms, including chemical energy, nuclear energy, gravitational energy, and stored mechanical energy. Chemical energy refers to the energy stored in the bonds of atoms and molecules. Batteries, biomass, petroleum, natural gas, and coal are all examples of stored chemical energy. Chemical energy is converted into thermal mass when we burn wood in a fireplace or burn gasoline in a car's engine. Nuclear energy is energy stored in the nucleus of an atom, the energy that holds the nucleus together. Very large amounts of energy can be released when the nuclei are combined and split apart. Gravitational energy is energy of place or position. It arises because of gravitational force where matter attracts other matter. When a gravitational force acts on a body and causes it to move through some distance, the gravitational energy is the gravitational force multiplied by the distance through which the body is moved. The higher and heavier an object, the more gravitational energy is stored in that object. Think of an example of a hydropower station. The higher and heavier the object, the more gravitational energy is stored in that object. The higher and heavier the object, the more gravitational energy is stored in that object. Think of an example. The higher and heavier the object, the more gravitational energy is stored in that object. Think of the example of a hydropower station where water sits in a dam. When a pipe is opened leading down towards the earth, the gravitational force drives the water through the pipe, which drives a turbine, which then generates electricity. Thus, the energy changes from gravitational to motion to electric. Stored mechanical energy is energy stored in objects by the application of a force. Compressed springs and stretched rubber bands are examples of stored mechanical energy. Kinetic energy is energy in motion. Some examples of motion are waves, electrons, atoms, molecules, and substance. It exists in many different forms. Thermal energy, or heat, is the vibration and movement of the atoms and molecules within substances. As an object is heated up, its atoms and molecules move and collide faster. Geothermal energy is the thermal energy found in the earth. Radiant energy is electromagnetic energy that travels in transverse waves. electromagnetic or EM radiation can be considered a stream of photons, and radiant energy can be viewed as the energy carried by these photons. Radiant energy includes visible light, X-rays, gamma rays, and radio waves. Sunshine is considered radiant energy, which provides the fuel and warmth that makes life on Earth possible. Motion energy is energy created by the movement of objects. The faster they move, the more energy is created. Wind and hydropower are examples of motion energy. Electrical energy is the result of an interaction between subatomic particles with electromagnetic force. Electrical energy is delivered by tiny particles called electrons, typically moving through a wire. Lightning is an example of electrical energy in nature. Sound is the movement of energy through substance in longitudinal waves. Sound requires some other kind of energy, such as mechanical, to produce a force. For example, when we yell. Sound energy may be converted into electrical energy for transmission, and later the electrical energy can be converted back into sound energy at the receiving end. For example, such as transformations could be seen in a microphone and a loudspeaker. One important property of energy is its ability to change from one form to another. For example, when you switch on a torch. The potential chemical energy in the battery is converted into kinetic electrical energy, which is finally converted to the desired form, radiant energy, as visible light. A car engine burns gasoline, converting the chemical energy in gasoline into mechanical energy. Solar cells change radiant energy into electrical energy. Energy changes form, but the total amount of energy in the universe stays the same. This is known as the law of conservation of energy. As well as being defined by its state, energy can also be graded by its potential to be productive. A high grade of energy exists where the energy is concentrated in a small space, for example, electrical and chemical energy. High-grade energy, like electrical, is best used for high-grade applications, like melting metals, rather than simply heating water. Low-grade energy, such as heat, can still be used to do work, but rapidly dissipate. This is because energy is stored in molecules, such as air or water, that are more randomly distributed or disordered than the molecules of carbon in coal, for instance. Measuring energy. Beyond simply classifying energy, there are numerous ways of measuring or quantifying energy. The standard unit of energy measurement defined by the SI system is the joule, written as a capital J. It is equal to the energy expended, or work done, in applying a force of 1 Newton through a distance of 1 meter. 1 joule can raise 1 kilogram of weight approximately 100 centimeters vertically, or in heat terms, raise 1 milliliter of water a quarter of a degree in Celsius. The use of energy is so various and occurs over such a vast number of scales that it is necessary to assign prefixes that can be appended when dealing with large or small values of energy, such as kilojoule, megajoule, or gigajoule. Other common units of measurement include British thermal unit, the kilowatt hour, and 2 types of calorie. One lowercase calorie is defined as the amount of energy required to raise the temperature of 1 gram of pure water by 1 degree Celsius. When the uppercase C is used, it is defined as the amount of energy required to raise the temperature of 1 kilogram of pure water by 1 degree Celsius. It is sometimes known as the dietary calorie. Converting energy measurements. The table shown here should allow you to convert between the more common units of energy measurement. For example, to convert 1 British thermal unit to kilowatt hours, multiply 1 by a factor of 3,412, so we can see here that 1 BTU is equal to 3,412 kilowatt hours. In conducting energy-based assessments, it's important to understand the relationship between energy and power, and in turn, their relationship with cost and efficiency. The common language used to describe energy and power can lead to confusion. Energy is a quantity, power is a rate. Often the term power is used when we mean electricity. The power bill from the local electricity utility is actually an electrical energy bill, which is based on the total amount of energy used for a period of time. Different types of energy are often measured in different units. Natural gas, LPG, diesel, and heat energies are measured in megajoules, whilst electrical energy is measured in kilowatt hours. Power, which is typically measured in watts, is calculated through the equation P equals E over T, or power equals the quantity of energy divided by or per time. For example, 1000 watt motor will use 1000 joules per second. This formula can be rearranged to express energy being the product of power and time. So, this tells us 1 watt is equivalent to 1 joule per second. When dealing specifically with electrical energy distribution and consumption, it is commonplace to use kilowatt hours as the unit of measure rather than joules. It is important, though, to note that the kilowatt hour and joule are different representations of the same thing, energy. An easy trick to remembering the relationship between energy, power, and time is the energy triangle. Here we see power is an expression of energy over time, and vice versa, energy as power by time, meaning that time then is an expression of energy divided by power. This power conversion table works in much the same way as the previous table, and it's a good idea to keep these on you in an audit situation. When calculating the usage of an appliance or system, it is not enough to simply calculate its idealized power. You must also account for the efficiency with which the system runs. The efficiency of an energy conversion process is the proportion of input energy which is converted to useful energy output. It is defined mathematically as the useful energy output divided by the total energy input. We will go into the relationship between efficiency and power shortly. Perhaps the most important relationship to understand when performing an audit is the relationship between energy, power, and cost. Given that we are concerned with promoting the efficient use of electricity to save money and reduce pollution, let's look at how energy efficiency relates to the cost of electricity. If the cost of energy per annum is equal to the product of the annual energy use of the per unit, and the energy use is equal to the product of power and time, then the amount you are liable to pay to your retailer is the total amount of energy units which you have used over the year in kilowatt hours multiplied by the hours you used it for, again multiplied by the price per kilowatt hour. To expand one more level, we also know that energy is an expression of the power divided by the efficiency of the system multiplied by a unit of time. This is the basic equation that we will be referring to for the remainder of the modules. Power here refers to the maximum active power that a device will output. System efficiency, represented by the Greek letter eta, is expressed by percentage, with 1 being 100% efficient and 0.2 being 20% efficient. Time is defined in hours. This formula is then an expression of the energy required to run a system at a particular efficiency over a yearly period. and can be used to see how much you could potentially save by increasing the efficiency or decreasing the time of use. It is important you understand that as it forms the basics of exploring energy efficiency in its many applications throughout the rest of the course. Using the concept of the energy triangle, let's look at the cost being a product of the energy and rate. When looking at the electrical energy, cost is expressed as dollars per year, found by multiplying the total kilowatt hours of the year by the rate, or tariff set by the retailer. Below that, energy can be calculated as the product of power and time. As discussed, electric energy is generally expressed as kilowatt hours, determined by the power in watts multiplied by the time in hours. The rate is determined by time in hours and quantity of kilowatt hours. And finally, power can be calculated as an expression of capacity and efficiency expressed as a percentage. Electrical energy is not the only form of energy you will encounter in an audit situation. In fact, electrical energy is often the result or requirement of another energy process such as heating. Specific theory and equations will be offered by section, where relevant, as you continue through the energy sessions. To continue with presentations, please select Energy Session 2.0 Renewable Energy Solar PV from the navigation bar. To complete the energy assessments for this presentation, please select Tutorial 1.0 Energy Basics.